Okay, welcome back. It's Mrs. Allen, and we're talking about related rates, and we're in section 2.8. This is the last section of the chapter, and we want to work on profit equations, profit functions. So in example 5, we're analyzing a profit function. The company's profit P in dollars from selling X units of a product can be modeled by this particular equation. Notice the capital P because we use lowercase p for demand. So P is equal to 500x minus 1/4 x squared. And the sales are increasing at a rate of 10 units per day. Find the rate of change of profit with respect to time in days when 500 units are sold. So what we have to do is we're going to implicitly differentiate on the left and the right. We're going to take the derivative with respect to time. But I always think one of the healthy practices, actually it's in life and in mathematics, is you begin with the end in mind. So in the end, remember, it says, find the rate of change of profit with respect to time in days. So we're looking for dPdt, and we want that to be the change. So it's going to be money over time. And time is going to be in days when 500 units have been solved. So if you look at the notation I have given you here, we've got dPdt with that vertical line, which means such that we want to find dPdt evaluated at x is equal to 500 and dxdt is equal to 10, and it's 10 units per day. So here we go. ddt of P is equal to ddt of 500x minus 1/4 x squared. So on the left-hand side of the equation, we get dPdt. On the right-hand side of the equation, we're going to get 500 dx dt minus, then we have 1/4 times 2 is 1. 1/4 times 2 is 1/2. So that's going to be 1/2 x. And then it'll be dx dt here also. So we factor out 500 minus 1/2 x, and then we factor out the dx dt. So we get dPdt is equal to 500 minus 1/2 x dx dt. So all we have to do here is just plug in our information. But if you notice this, just an evaluation of this function itself, and you could use a graphing calculator, but I thought I'd save you the time. So here you have your profit function. And when there are 500 units sold, the profit is $100, and I have it down here, $187,500. Okay, so at that point, you can see that we have the slope of the function there. That slope would not represent what we're talking about in this problem because we're talking about dPdt. So I want to just point this out. It wouldn't be this tangent line we'd be looking at because that would be a dPdx. Okay, so what we have to do is just plug in here. So we have dPdt is what we're finding is equal to the quantity 500 minus 1/2. And when there are 500 units sold, so we want to put the 500 in here, and our dxdt is 10 units per day. So we're going to put that in as 10. So we get dPdt is equal to 500 minus 250. So that's going to be 250 times 10, which is 2,500. And that would be in dollars per day. And there would be your answer. Okay. There you go. There you have it. There it is. Okay. Oops. Okay, so that's example 5. Example 6, increasing production. A company is increasing the production of a product at the rate of 200 units per week. The weekly demand function is modeled by P, it's a lowercase p, is equal to 100 minus 0.001x, where P is the price per unit in dollars, and X is the number of units produced in a week. Find the rate of change of the revenue in dollars with respect to time in weeks. So when the weekly production is 200 units. Okay, so the weekly production is 200 units. So that kind of gives you a rate. If you think about that, that's going to be a rate. Here, let me lower this a little bit. Okay. Okay. So in the end, we want to find DRDT in dollars per week. Okay. If you think about it, X is the number of units produced in a week. So everything is in terms of weeks already. So in the end, we want to find DRDT and then in dollars per week. So our equation then is is equal to XP. That's our revenue equation. Think about this. The number of units sold, the revenue, times the demand in price per unit. So units for X, here's our X, and then P is in dollars per unit, and the units cancel and you're left with dollars. So there again you would see a clear understanding of, if you're going to write an equation, you want to have a unit analysis that you understand. So the revenue is equal to X times 100 minus 0.001X, and we could distribute that X, 100X minus 0.001X squared. And now we're going to take the derivative. We're going to take we're going to take the derivative with respect to time. So the derivative with respect to time on both sides of this equation. On the left, we have the derivative of R. On the right, we take the derivative of 100x minus 0.001x squared. So on the left, we get what we're hoping to find is our dr dt is equal to 100 dx dt minus 0.002 x dx dt. And then let's go back and see what information that we gleaned from the problem. So we want, when there's a weekly production rate of how many units per day, right? So we need the units per day. And we know that that's going to be our dx dt. So that looks like it's 2,000. Oh, units per week. I'm sorry. I said day. Units per week. And that's going to be 2,000. And then we have the demand. So we have the rate. We're going to make 200 units per week. So it's the rate of 200 units per week, but X at this case is going to be 200. Even though it sounds like it's a rate, it does. It's a production of the rate of 200 units per week. 200 units per week. And then the weekly production is 2,000 units. Did I say that backward? 200 units per week. And the weekly production is 2,000 units. So here we go. So the weekly production is 2,000 units. Sorry about that. Let me just make sure. Let's make sure that we have everything. A company is increasing the production of a product at a rate of 200 units per week. So here's a rate. This is going to be our dx dt, where P is the price per unit in dollars and X is the number of units produced in a week. Find the rate of change of the revenue in dollars with respect to time in weeks when the weekly production is 2,000 units. So sorry about that with the 200 and the 2,000s. I got that mixed up, but here we go. Kind of doing this cold, but I think we got it. Okay, so now we want drdt. So we got drdt is equal to 100 times dx dt, which is 200, minus 0.002, and then that would be times x, which is 2,000. And then we have times dx dt again, which is 200. So we get 100 times 200. So it's 200 and add 2 zeros, 20,000. Minus then if I have 2 times 2 is 4. So I end up with moving this, if I multiply by 2,000, if I multiply by 1,000, I would just get 2. But because I'm multiplying by 2,000, I get 4 times 200. So I end up with dr dt is equal to $20,000 minus, it looks like $800. I'm going to go back and check all the math here because I'm just doing this on the fly. So we get $19,200 per week. So not a bad little pocket change, but let me see. All right, so this is again in this section, unrelated rates and other applications. So this will be a problem that I think that you'll be a little bit more familiar with because of the problems we've done in the past with revenue. Okay, and so example 5 and 6, that'll be the part 3 video, and this completes my video at this point for section 2.8 that matches along with your notes. So what you probably want to do next is go ahead and do the problems that are in your checkpoint. Okay? All right, well, you guys have a great day, and I will see you soon. Take care.